All right. We're talking about carboxylic acids and their derivatives, and just for to set the stage, we have carbonyl compounds here. We know our aldehydes and our ketones, and then we have all of these structures shown here, which are known as acyl derivatives. So we have our carboxylic acid, or ester, or anhydride, or acid chloride, and our amides, or primary, secondary, and tertiary amides. What's the difference between carbonyl compounds and acyl derivatives? How do we know how to categorize them? Anybody? No one?
Miss Brown, can you repeat the question, please?
I'm asking what's the difference between carbonyl compounds and acyl compounds? So in the box at the top, those are examples of compounds that are referred to as carbonyl compounds. And that's what was our last topic. We spent a lot of time talking about carbonyl compounds. Now, these structures also have a C double bond O in them, yet they're not referred to as carbonyl compounds. How do we know what's the difference? Nadisha is saying has OH attached to carbonyl group. That's a carboxylic acid, yes. Carbonyl to different functional groups. Sinead, do you want to expand a little bit on it? One wants to expand. Go ahead.
What I was trying to say is that I noticed that for the aldehyde and the ketones, it's like an R group, either an R group or the hydrogen. But for the acyl compounds, they are attached to different functional groups along with like another.
Okay, yes, I'm getting what you're saying. And that's correct. So if we look at our aldehyde and ketone, as she said, it's either going to be a hydrogen or a carbon that's attached to your carbonyl groups for your carbonyl compounds. But for your acyl derivatives, what we have is a variety of different functional groups. But the key thing is that they're heteroatoms, right? So in our carbonyl compounds, it's either going to be a hydrogen or a carbon that's attached to the C double bond O. But for acyl derivatives, which is the big category that all of these structures fall under, it's going to be the carbonyl attached to a heteroatom. So for the top row, we see that oxygen is the heteroatom that's attached to the carbonyl group. For acid chloride, as the name suggests, the chloride is attached to the carbonyl group. And for our amides, it's going to be nitrogen. That's how we know how to categorize what is what. And because it is the different connectivity is going to mean different properties between carbonyl compounds and acyl. There will be some similarities, but there are also some differences due to these heteroatoms. All right, so this is what we're going to go through. We're going to just very, very briefly touch Nadisha's question. Yes, you can. You can have acid bromides and acid iodides, but they're not as common. So they are possible, they do exist, but the acid chlorides tend to be the most common ones. Yes. So we're going to look at naming very briefly. We're veterans at naming, so we don't need to spend too much time. We're going to look at acidity of carboxylic acids and things that influence acidity, how we make our carboxylic acids, and then we're going to look at some reactions. And generally, this is the reaction mechanism that you're going to see over and over again. All of our acyl derivatives, they follow this pattern, right? So where I have Lg, that refers to leaving group, and Lg is usually the heteroatom that's attached to the carbonyl in our acyl derivative. And for all of our acyl derivatives, you will have a reaction where a nucleophile comes in, and you have addition, and this is the intermediate that's formed after the addition, and this intermediate will reform the carbonyl, and you will have elimination. You will have loss of all of this here, and then you get a new compound here. So that's generally the reaction mechanisms for all of our acyl compounds. So we're going to be looking at that. All right, so straightforward naming for our carboxylic acids. You look at the number of carbons, you'd find the parent alkane, you drop off the E, and you just add oic acid. And then we know that in terms of numbering or functionalities, that the carboxylate group, that is the C double bond O that's attached to the OH. So all of this is the, let's clear that off and try it again. All of this is the carboxylate group, all right? That carbon is going to be numbered 1, and everything else is going to be numbered with respect to it. So methanoic acid, ethanoic, butanoic, and notice that this is 3,3-dimethyl. It's not 2,2 because we're going to start counting from the carboxylic group. And then we have this aromatic carboxylic acid, benzoic acid. And you'll be doing aromatic chemistry. I think that's our last topic if we get to it. And then you'll look more at aromatic structures. So we just drop off the E and we add oic acid. All right, so like any acids, carboxylic acids are proton donors. And so when you dissolve them, you have an equilibrium set up where this OH bond breaks, it donates a proton to, say, a molecule of water, and then you form your carboxylate ion and you have your proton here. And when you did analytical chemistry and you were looking at acidity and Ka and all of those things, you knew that the Ka is going to be products over reactants, right? And the Ka is a measure of to what extent the equilibrium is shifted either to the left or to the right. If we have a large Ka, it means that we are mostly to the right, and we have dissociation almost completely occurring. And if we know that if we have a large Ka, we're going to have a small pKa. And pKa is usually the factor that we use to describe acidity for our carboxylic acids. And we know just like pH, the lower the pKa, the stronger the acid. And some other terms that we want to remember, that the acid, once it has lost its proton, it is now known as the conjugate base. So the carboxylate anion is the conjugate base of our carboxylic acid. So we're just trying to remember all these terms that we learned from analytical chem. Right. So as we can see this equilibrium here, anything that allows us to generate more protons is going to increase the acidity of carboxylic acids. So anything that is going to have this equilibrium shifting more to the right means that there's more protons being released. More protons being released, you have greater acidity. And so if there's something that weakens this OH bond, because this oxygen-hydrogen bond has to break in order for the proton to be released, any factor that weakens the OH bond is going to enhance acidity. And then anything that reduces the negative charge on our carboxylate anion is also going to increase acidity. So let's look at that. If it's an equilibrium, sorry, go ahead, Jordan, ask your question.
Good afternoon.
Good afternoon.
All right, miss. You know that I'm just asking a question about relating to what you're doing now. You said acidity would increase, miss, the more to the right the reaction wants to proceed, right, miss?
Yes.
So you're saying that anything that weakens the OH bond will mean that it readily gives up, the carboxy readily gives up the hydrogen, which makes it a good acid, right?
Yes.
Okay, miss. And you say the weaker the negative charge, right? That means say if it weak, miss, it does not want to form back a hydrogen bond with another hydrogen, so it would turn back the equilibrium to the left, right?
Right. So if to go back to the left, we have to reform the oxygen-hydrogen bond. So anything that interferes with the ability to reform the oxygen-hydrogen bond means that the proton stays out there and that the acidity is increased. So yes, you're correct. All right. So if we reduce the negative charge density that's around this carboxylate group, it means that these electrons are going to be less available to reform the OH bond to give us back the parent carboxylic acid. So anything that reduces the negative charge is going to mean that the proton stays in solution longer and we're going to have enhanced acidity. So we're going to look at the features that influence the strength of the OH bond and the negative charge density on the carboxylate ion. So first is solvent. So depending on what you dissolve your carboxylic acid in, the acidity is going to be different. So we're looking at the carboxylate anion of acetic acid or ethanoic acid, same thing, in water versus in ethanol. So as it states here, that in water, this negative charge density on the carboxylate ion is dispersed. It's spread out more because you have more interactions between this negatively charged carboxylate and these dipoles in the water molecule. So we know that water molecule is going to have a region that's delta negative and a region that's delta positive. And this delta positive region of the water molecule can interact with the carboxylate, and it helps to sort of spread out the negative charge as these several water molecules interact with our carboxylate. If the negative charge is busy interacting with these water molecules, it is less available to reform the OH bond, and so acidity, the equilibrium is to the right. Looking over here, we have ethanol. Ethanol is also polar, but we know that it doesn't have as much of a dipole as water. Water has these two polarized OH bonds. Ethanol has only this one right here. And so the negative charge is going to be less dispersed in ethanol compared to water. And you can see there's a marked difference in acidity when an acid is dissolved in water as opposed to dissolving in ethanol. So solvents can influence acidity. Okay, go ahead, Noelisa.
Brown, sorry, I didn't catch that. You said it'll be more acidic in the water?
Yes.
Okay, thank you.
Yes. Oh, it was just, that was the question, or you wanted to?
Yeah, I just never heard what you said.
Okay. Yes. All right, Shanae, go ahead.
Miss, could you just go over that once more, please?
Okay, sure. So remember, to be an acid, the species has to donate a proton, but there's also an equilibrium set up. Because you have this negative charge and you have this proton, you could reform the OH bond, and once you reform the OH bond, you're reducing acidity. Because the whole concept of acidity is being able to donate a proton, being able to give a proton. So if it is picking up back the proton, then acidity is not happening. When you dissolve a carboxylic acid in water, and you have the first separation of the carboxylate and the hydrogen, that OH bond is broken. In order for it to be reformed, you need to have interaction between this negatively charged carboxylate and the positively charged proton, right? But having these polar water molecules surrounding the carboxylate anion is going to reduce and interfere with the reforming of the OH bond. It's going to reduce and interfere with the attraction between the negatively charged carboxylate and the proton that is out there in the solvent. And so because the water molecules are interfering with reforming of the OH bonds, it means that acidity is going to be good in water. Compared to ethanol, which is a less polar solvent, we only have one significantly polar OH bond here. The interactions between the carboxylate and the ethanol molecules are going to be less than the interactions in water. And so you have this negative charge that is more available to reform the OH bond. So acidity in water is going to be much greater, up to 10 to the 5. That's a pretty big number. 10 to the 5 times greater in water than it is in ethanol. Right? Did that help, Shanae? Yep. Okay. All right, cool. So if you dissolved your acid in different solvents and you measured the pH, you would get different values. That's essentially what we're saying. All right, but more importantly, let's look at the structure of the molecule and how it influences acidity. The more electron withdrawing groups that you have attached to this carboxylate, it is going to increase acidity, right? Can anyone sort of walk me through why. How does having an electron withdrawing group affect anything? Yes, go ahead, Jordan.
All right, miss. So you know, say with a electron withdrawing group, you know, say them have a negative inductive effect. So that means
Mhm.
it would have a greater tendency to pull electrons within the bond between itself and hydrogen. So therefore, it will kind of weaken the bond and make it
Uh-huh.
less easier for the H plus H, the hydrogen atom to be broken up and released and form an acid or
Right. Would it,
increase the acidity. That's yeah, increase the
right. It
acidity.
would be easier. Okay. So let's look at all the points that Jordan raised. First, we know that electron withdrawing things are going to be electronegative, right? And electronegative means that it pulls electron density towards itself. Now, if it is a group is pulling electron density towards itself, then it's going to help to weaken this OH bond. Remember, we talked a lot about the inductive effect when we were looking at the acidity of carbonyl compounds, or when we were looking at the Wittig reaction, why it is that this carbon-hydrogen bond is all of a sudden acidic. It's a similar thing. If you have a group pulling electron density from this carbon is now going to pull electron density from this oxygen, and this oxygen is now going to pull electron density from this hydrogen. And all of this pulling and this uneven distribution of electron density is going to result in a more polarized and a more weakened bond. So having electron withdrawing groups means that you have inductive effect, and the greater the inductive effect, the more electron density is being pulled away from this carbon-oxygen bond, and the more electron density is being pulled away, it means that the weaker and more polarized this OH bond is. And so we have some examples on the screen looking at various carbon acids. Yes, go ahead, Michaela. Michaela?
Miss, you hearing me?
Uh-huh.
When we were doing Wittigs or whatever her name, Miss, we were talking, or no, not that, Miss, when we were talking about how carbonyl compounds can be used to form nucleophiles, weren't
Uh-huh.
we were talking that we were saying that the oxygen, the oxygen that's double bonded to the carbon, it pulls electrons away. So wouldn't
Right.
that also contribute to the inductive effect as well?
Sure, but in all of them, all of them have that constant,
Oh,
right?
okay.
So all of them have a carbon-oxygen bond. What we want to look at, and so you are correct. This carbon-oxygen bond is also pulling electron density from this carbon-oxygen bond here. But what we want to look at is what is different as we go across the fact that the pKa is getting lower and lower and lower. So that is the part we want to focus on. But yes, you're correct. That is also a part of the electron withdrawing effect. So if we look at these acids, we have acetic acid, which we know is vinegar, and it has a pKa of 4.74, and you know it's fairly safe to handle. Nobody ever, well, that's not true. The vinegar is a solution of acetic acid in water. Full strength acetic acid is not the most pleasant, but it wouldn't do much to you. Just smells bad. And then we notice that as we replace a hydrogen with a chlorine, we've gotten chloroacetic acid. Some fell down. What? No, Elisa, what were you doing? Let me, I don't know why I'm laughing. Sorry. A hydrogen is replaced by a chlorine. It is pulling electron density. So the inductive effect that Jordan was talking about, we're starting to see it. And notice pKa has dropped. It's dropped from 4.74 to 2.86. So we know that chloroacetic acid is much more acidic than acetic acid. And that's just by replacing one chlorine, we've dropped the pKa by a unit and change. Now look, when we add two chlorines, dichloroacetic acid, we see that the pKa has dropped to 1.26, which is a big difference from acetic acid. And then trichloroacetic acid, or TCA as it's commonly called at the spas or the aid stations parlor, has a pKa of 0.64, and that's used when persons do skin peels. So when persons want to look at young, rejuvenated skin or what have you, they're using an acid that's so strong that it's dissolving the outer layer of their skin, that it can be scraped off to show new skin underneath. And we see that just by changing a hydrogen and swapping it out for a chlorine, we have drastically altered the acidity. Listen, TCA is big business. People who are not chemists are making money just understanding some of these things and using them to do what they need to do. Actually, Shanae, bleaching cream works by a slightly different method. Most bleaching creams are reducing agents, and so they reduce the pigment in your skin, but people do combine the two, so they lighten and strip their skin at the same time. It's a thing. It is a thing. Yes, it is. Yes, indeed. Yes, Jordan, go ahead.
It's a question, miss. So for like electron donating groups such as methyl group, miss, suppose they had surrounded the carbon of the two chlorine.
Carboxylic acid. I
That
am
would
just
kinda
about
reduce.
to do that.
Oh,
Go ahead.
okay. That would
No,
reduce
go ahead.
it would reduce the acidity, miss, because
Yes.
it would push electrons towards the carbon, and you'd have
Right.
like a buildup of charge there. So
Correct.
yeah, okay.
Correct. So he is quite correct. If electron withdrawing groups increase acidity, then it stands to reason that electron donating groups are going to decrease acidity, right? Similar things. The inductive effect with the electron withdrawing group is to pull electron density away. With the electron donating up groups, it's going to be pushing electron density to our carboxylate group. So let's look at some examples. So here we have methanoic acid, which is also known as formic acid, and we see the pKa here, 3.75. But as you replace a hydrogen with a methyl, notice that the pKa is increasing, and an increasing pKa means that the acidity is decreasing. And similarly, if you replace some of these hydrogens on this carbon with methyls, then we see another significant drop in acidity because the pKa is increased. So methanoic acid, we would know, people would experience methanoic acid, also known as formic acid, when an ant stings you and that burning sensation, the ant has released formic acid to your skin, and so that's why you feel the pain, right? So the ant has essentially doused you with acid in terms trying to defend itself. Yes, that is why it burns. It's formic acid. That is what the ants are releasing, and we see they're strongly acidic, more acidic than acetic acid, right? Okay, so by manipulating the groups, we can manipulate the acidity, and so you can design acids for whatever purpose you need by manipulating the groups. It depends. Some bees have venom, which is different from acid. The venom are these little tiny peptides that irritate your skin and initiate a reaction. So I think most bees have venom, whereas many ants and other insects have acid that they release. All right. So we know that given a question in terms of comparing the acidity, we're going to look at the groups, whether they're electron donating or electron releasing. All right, so we've looked at naming, we've looked at how structure and solvent influence acidity. Let's look at how we make the carboxylic acids, because we just said that by tweaking conditions and designing acids, we can get particular applications. So let's look at how we make these acids. We already know the first two, they're more revision, and the third one is slightly new. So we know that oxidation can give us carboxylic acids. Carboxylic acids are the most oxidized product. So you can start from an alcohol or aldehyde or alkene and oxidize up to a carboxylic acid, or you can do a Grignard reaction. So let's look at these. If you treat your alcohol or your aldehyde with any of these oxidizing agents, so we know if we have acidified dichromate, it is going to oxidize all the way up to the carboxylic acid. If we have acidified potassium permanganate, the same thing is going to happen. So both our alcohol, so we know it's a stepwise thing where the alcohol will be oxidized to the aldehyde, which then goes to the carboxylic acid. And then we know that alkenes, that we can cleave the double bond using hot acidified potassium permanganate, and it can give us the carboxylic acid. Is there another reagent that we know that can cleave a double bond and lead to a carboxylic acid? Yes, correct, Nadisha. So ozone ozonolysis can cut our double bond, and depending on workup, because remember we have reductive workup and oxidative workup. And so if we use oxidative workup, we get our carboxylic acid. So these are ways that we know to make our acids. Note that if you're using your alcohol and your aldehyde, then your acid has the same number of carbons. But if you are starting from an alkene, of course, your acid is going to have less carbons because you have split your alkene into smaller fragments. So that's always something to remember. All right, from Grignard reagents, we know that we can start with an alkyl halide, we can react it with magnesium, and then we can generate a nucleophile, right? So we have generated our Grignard reagent right here, and we know that the R magnesium bond is nucleophilic because the carbon is going to be more electronegative than the magnesium, and so the carbon can act as a carbon nucleophile from the Grignard reagent. Or electrophile happens to be carbon dioxide. So looking at carbon dioxide or C double bond O and a C double bond O, we can see that this carbon is very delta positive, and so it's a good electrophile. And so if we're looking at our mechanism, our nucleophile comes in to our electrophile, you're forming a bond, you're also breaking a bond, and this is the intermediate or alkoxy intermediate that we have here. We know that whenever the Grignard reacts, there's an intermediate, that O magnesium bond, and to get rid of this, you add some acid and water and you protonate. So that we are familiar with. And this is an example where we have an aromatic alkyl halide. We react it with our carbon dioxide, and we end up with benzoic acid at the end of the reaction. And this one is different now. When you're doing the Grignard reaction, your acid is going to have one carbon more than what you started with. Because remember, you're reacting it with CO2, and that becomes incorporated into the new molecule. So the chain is lengthened by one carbon. All right, so we have hydrolysis, which is not really new to you, but this is another way of making our carboxylic acids, which is a little bit of a waste because we use carboxylic acids to make all of these compounds that we're hydrolyzing, but I digress. Hydrolysis, we know that the term means that you're using water to split something apart. And so for ester, or ester has this functionality, C double bond O attached to oxygen, and this oxygen is also attached to some carbons. So that's our ester functionality. Remember, we said all of our reactions of our acyl derivatives is a nucleophile coming in and displacing this group here, this leaving group. So if our ester is hydrolyzed, we lose all of this and we replace it with water, and we get our carboxylic acid. And hydrolysis can occur in either acidic or basic conditions. And we're going to talk about that a little more in a bit. Similarly, our amides can undergo hydrolysis to give us our carboxylic acids. And so we know whenever we eat and food is in our stomach, this is what's going on. Our body is hydrolyzing all of the things we've consumed and breaking them down into smaller things that we can use for energy. So this amide hydrolyzed, this group is replaced with the OH from the water, and we have our carboxylic acid. Our acid halide can also undergo hydrolysis. Remember, X could be a chlorine or a bromine or iodine, as was pointed out earlier, and what comes in and replaces all of that, we get our acid. We have our anhydride, water comes in and replaces all of this, and we get our carboxylic acid. So there are many ways that we can break down an acyl derivative to give us our carboxylic acid. Then for nitrile, it's a little bit different. Nitrile, there's no leaving group, but what you're having is an addition reaction, where we see that water can act as a nucleophile, it can add, and we form an intermediate that is still electrophilic, and water can go in again and add, and at the end of the day we have our carboxylic acid and or ammonia. Our nitrogen is going to leave as ammonia. So if you're ever asked to make carboxylic acids, you have ample methods, just depends on what it is that you want or what you're required to start with. All right, so are there any questions so far? Because now we're going to move in the mechanism section of things. Any questions about acidity, about structure, about how we form carboxylic acids? All right, so it seems that we are following so far. All right, just a refresher. Sometimes we get confused because our carbonyl compounds look similar to our carboxylic acids, and we think they behave exactly the same, but we have to take note that, remember, in our carbonyl compounds, we have either a carbon-hydrogen or a carbon-carbon bond, and that is the reason why there's all the difference. So we know that if we have this ketone here, and there's a nucleophile, whether the nucleophile is an alcohol or an amine or whatever, we have our addition reaction taking place, where we're forming a carbon nucleophile bond, and we're breaking this carbon oxygen pi bond, and we also form this oxygen hydrogen bond. So this is the addition reaction for our carbonyl compound. But for our carboxylic derivatives or our acyl derivatives, the names are used interchangeably. We do have addition happening first. So we have our nucleophile coming into our electrophilic carbon, and we form this tetrahedral intermediate. So it's similar here, but there is going to be a difference in that we can reform the pi bond because we have a good leaving group. And then we form this structure here. So the difference in an addition reaction, you're moving from sp2 to sp3. So from double bond to everybody's single bonds, and the reaction stops there. For our carboxylic derivatives or our acyl derivatives, we do form an intermediate that has only single bonds, but we are able to reform the sp2 hybridized bonds because we have a good leaving group. So let's look at that a little bit more. All right, so this is our intermediate from our carboxylic derivative that we just showed a while ago. So our nucleophile has added, we've broken our carbon-oxygen bond, and we have this carbon-OH bond here. And this is the intermediate from our carbonyl when our ketone reacts. Notice that we have a polarized bond here, whereas we have a non-polarized bond. This would be a carbon bonded to carbon. Polarized bonds are weakened because electron density is unevenly shared, whereas bonds like this are strong. We have an even sharing of electron density. And so we are able to reform our carbonyl and break this bond, whereas the energy required to do this is not going to happen. And so for our carbonyl compounds, it's going to stay at this intermediate. You're just going to protonate the oxygen at the end of the day. But for our acyl derivatives, we are going to reform the carbon-oxygen double bond, and we're going to lose this group. And our reaction conditions will convert this into a good leaving group. All right, so that was the general discussion, and now we're going to look at some specific examples, and let's see if we're seeing the patterns repeating over and over in terms of the mechanism. The mechanisms for these carboxylic acids and their derivatives is going to be addition followed by elimination. And so at the end of the day, you should reform your carbon-oxygen double bond. And if that's not happening, you need to check and see where you kind of went wrong. So first, esters. We just spoke about using esters to form carboxylic acids, but we know that we react carboxylic acids with alcohols in order to form our esters. And this is a reaction that you should be fairly familiar with. Let's track what's happening. We have our carboxylic acid, we have our alcohol, this is methanol, we have our acid catalyst, and then we form our ester. In this reaction, which one is going to be our electrophile, which one is going to be our nucleophile? Anybody?
The carboxylic acid will be the and the alcohol will be the nucleophile.
All right, so our carboxylic acid is going to be our electrophile and the methanol, and we see it in our product. Notice that this part of the molecule is conserved. This part stays. All we've done is replaced our OH with our nucleophile, essentially, right? So we had our alcohol come in and it replaces this OH to give us our ester. So let us revise the mechanism, which looks a little long and convoluted, but not really, not really. All right, so you're going to help me to, yes, Kasela, go ahead.
Good evening, Miss.
Good evening.
Can you go back to the previous slide, please?
Yes, this one?
Right.
Or the, yeah.
I don't understand. We're saying that the OH group leaves over the
Yes.
right-hand side, but I'm seeing where the addition part is being added over to this carbon over here.
Wait, let's go again. So let me draw. So what's going to happen is that this oxygen is going to come here. And as we're forming this bond, eventually we're going to break this bond and all of it is going to leave. So the oxygen that you see in the product has come from our alcohol.
Okay.
Yes. Yes.
Okay.
Right. That's why I asked
Okay,
which one.
it's written a different way.
It's written. Oh, that's
It
what's
kind of
throwing
looks
you
flipped.
off. Okay, yes, sorry, yes. Okay, we should have been consistent in, okay, I see.
Oh, I understand, Miss. I understand
Okay,
now.
all right,
Thanks.
good. All right, so that's sort of the, not the trick, but that's one thing to watch for whenever you're doing reaction with acyl derivatives. Just know that whatever this group is, you're replacing it with whatever else you're reacting. So this is going to leave at some point, and your OH, your nucleophile, whatever it is, your nucleophile is going to replace your leaving group, whatever the leaving group is, whether it's an OH, whether it's a chlorine, whether it is a NH2, your nucleophile is replacing all of this. And so some textbooks, instead of referring to it as addition elimination, they like to refer to it as a nucleophilic substitution. Go ahead, Nadisha.
Miss, when you react the alcohol with the carboxylic acid at the slightly positively charged carbon, how do we get rid of the hydrogen that was on the alcohol?
Oh, we're going to show you in a bit. It's a step-by-step process where you'll have another molecule of methanol that can take that hydrogen away at the end of the day.
Okay.
Yes. All right. So let us go through, and you guys are going to help me with some arrow pushing here. So looking at this structure, we have our acetic acid, and we look at the intermediate. How would I draw the arrow to reflect the formation of this species here? Talk to me.
From the oxygen to the hydrogen.
All right, so we know that we form an oxygen-hydrogen bond. If our hydrogen is positively charged, it means that the electrons must have come from our oxygen here. So this is our nucleophile, this is our electrophile, we have formed this. Okay, good. Right, I forget that you guys can draw on the screen as well, no? Okay, so somebody. Methanol, no. Okay, before I even do that, how does protonation of this oxygen help the reaction to go along? What is it doing?
Would it make it more reactive? Because never mind.
Mm-hmm. Yes, it would make it more reactive because what? What's it doing?
Because like the double bond is going to break to supplement that positive charge, and then um okay, never mind. I lost my train of thought. I feel like it'll make
All
it
right.
more.
So it does enhance the electrophilicity. It makes this carbon more delta positive, right? Because if you have this oxygen that's positively charged, it's pulling electron density from this carbon. And we could draw a resonance structure. All right, so we could draw, let's put in my resonance arrow. We could draw a resonance structure where these electrons go onto the oxygen to quench this positive charge. Okay, let's see if I can get this looking fairly.
So then
So this is now, this should be a positive charge. And this is a CH3 over here. So we see that this resonance form helps us to recognize that protonation enhances the acidity, because we've moved from a slight positive charge to essentially a full positive charge right here. So protonation, wasn't that a question in the course test? Yes, I do believe it was. There was a question about a mechanism where you had to protonate a carbonyl, I do believe, right? We know that when we have weak nucleophiles, that protonation enhances this to make it more electrophilic, and that's how the reaction is able to progress. Yes, yes. So we have protonated, we have made this more electrophilic, and so our nucleophile can react. And so we show our lone pairs of electrons right here. We have our nucleophile coming in to our carbon. And we're forming a bond, we've broken a bond, and now we have an intermediate right here. So we've had the addition phase of the reaction. Now someone was asking, how do we lose the protons? This proton has disappeared. Where did it go? What could have taken it off? Yes, Shanae.
Miss, did the oxygen has a positive charge? So did the electrons from the hydrogen bond just so miss, you know what I mean? It
That's what you're going to write on the exam, miss, you know what I mean? But yes, I do know what you mean. So we know that the electrons in this oxygen-hydrogen bond are going to go onto the oxygen to quench that charge. But where did the hydrogen go? What took the hydrogen away? Anyone wants to guess? Go ahead, Joel.
Probably a methanol, miss. An ex-methanol, take it, miss.
Right, so we know that methanol is floating around with lone pairs, so it could have taken the proton and we would have lost it, and the oxygen would now become neutral because electrons have quenched the positive charge. Correct, correct, correct. All right, so we've done the addition part. Now let's look at the elimination part to reform our double bond, and that involves protonation again. Why do we have to protonate the OH? Why can't it just leave by itself and go about its business?
OH
Right. I'm not hearing you clearly. Go ahead. Hello?
OH is not a good leaving group.
All right, it's not a good leaving group, and we need to make it into a good leaving group. Remember, The reason why OH is not a good leaving group, if we break this carbon-oxygen bond, remember the more electronegative atom always takes the electrons. If we break this carbon-oxygen bond, we're generating hydroxide and a positive charge right here. You're going to have a negatively charged thing and a positive charge right here. A good nucleophile and a positive charge, the bond is just going to reform. OH is not going to leave and stay gone. Whereas if we protonate it, we formed water, which we know is going to leave as a neutral molecule, and it's going to be far less electrophilic. So correct, OH is not a good leaving group, and we must make it into a good leaving group, and we do so by protonation and or arrows. Remember, it's going to come from the lone pairs of the oxygen, and it is going to go to our H+. We've made it a good leaving. Yes, Jordan?
Again, miss. Before you even go no further, miss. Yes, you were saying it's not a good leaving group, right, miss? So you said it because oxygen electronegative, right? It will pull the electron density from the hydrogen to form an epoxide, right, miss?
No, for hydroxide. Hydroxide.
Okay.
Yes.
Right. So that means that any hydrogen represent the form like a bond with it, so to make it, and it will make it difficult to remove it. That I mean, miss?
Yes, I'm saying, so every bond breaking and bond formation is reversible at a level. So if I break this carbon oxygen bond right here, you're going to have O minus, and this is going to be positively charged, right? As soon as I break it, the negatively charged oxygen is going to be attracted to the positively charged carbon and reform the bond.
Okay.
Right?
All right.
But when you protonate it, it becomes a good leaving group. So it leaves and stays left, if you get what I'm saying. All right? So we've made it a good leaving group. And notice the difference in structure between these two. We have this tetrahedral, 4 bonds, and we have this trigonal planar, 3 sets of bonds. How do I push arrows to show that I'm reforming carbon-oxygen double bond? And remember, we're filling in all the arrows for a mechanism. Where is the arrow going to come from? Where is it going to?
Hold on at the bottom, miss. The OH, miss.
All right, so we know that we have electrons here, lone pairs on this oxygen. So we are going into form. This is supposed to be an arrow, hush. We're forming this carbon-carbon double bond, but if we're forming a bond, we need to be breaking a bond. And which bond is the most polar? Out of these 3 bonds, which is the most polar bond and which one is going to get broken?
Miss OH, miss.
One that has a positively charged oxygen,
yes,
right? So you always look for the most polar bond when you're trying to work out what, okay. And so this bond breaks and takes the electron. So now we have this structure right here. And then once again, we need to get rid of our hydrogen, and another methanol can come and get rid of the hydrogen, and it will donate electrons. Can I get it? Onto this oxygen so that it is no longer positively charged. And so notice we started with an acid and we have now formed an ester. And then all of this, or alcohol, was the nucleophile, and we lost the OH that was initially a part of the carboxylic acid. So our mechanism was addition followed by elimination. Yes, Nadisha?
Miss, what do you call the initial product formed?
What do I call what? Sorry?
The initial product that you form before you do the elimination.
This, which one? This one where the arrow, where my pointer is?
No, the next one with the methoxide group on it.
This one here?
First one.
Oh, the first one.
That one.
This is like a hydrate. This is like a hydrate of a carboxylic acid. I don't know if we really refer to it by name.
Okay.
It's like a hydrated acid. We don't give it a proper name because it's an intermediate. It's just a step in the reaction. It doesn't exist for very long. Does that answer your question, Anisha? Mm-hmm. It's
Yes, ma'am.
a hydrate of the carboxylic acid. And so we form our ester here at the bottom. So that's what we formed our product. All right, and so now we're going to look at the opposite of what we just did, but it's the same mechanism. You're going to have a nucleophile coming in, and you're going to have a group leaving. So before, when we were making the ester, it was the alcohol coming in and the OH leaving. When we're breaking down the ester, it is the OH coming in and the alcohol leaving. So it's essentially the same mechanism. All of them are essentially the same mechanism. A nucleophile is going to come in, we're going to have addition, and then we're going to have elimination to give us our product where we have reformed our carbon-oxygen bond. So same mechanism, just changing what the nucleophile is. In fact, with this ester, instead of hydrolysis, where we have hydroxide, we could have had an amine in the nucleophile, and the amine would add, and all of this would happen. At the end of the day, we would form an amide. So all of the mechanisms are the same. Nucleophile comes in, and the group that was attached to the carbonyl, it gets displaced to give us our product. And so you can spend some time practicing the mechanism, because once you know the mechanism for one, you essentially know the mechanism for all. Yes, repeating the same thing over and over. Protonation, nucleophile coming in, and we're losing a group. So once you can get the one for the ester, you can get the one for the other ones too. All right, so just to close off. Oh yes, go ahead, Nadisha.
This was the difference when you do a acid hydrolysis or when you use the OH.
Oh, so that's a good question. The only difference is when the proton gets added. So when you, let's go back. In base hydrolysis, notice we don't protonate first. This is just like our carbonyl chemistry, if you think about it. Remember, in our carbonyl chemistry, we can have the reaction happening under acidic conditions or under basic conditions. Once you have acidic conditions, the first thing that's going to happen is the oxygen is going to be protonated, and then everything else happens after. Once you have basic conditions, everything else happens first, and then the oxygen gets protonated afterwards during workup. So it's just the order of when the proton gets added to that oxygen.
Okay.
Yeah. All right. So base hydrolysis, you notice that there's no protonation at the start before, because you have a strong nucleophile that can react with our delta positive carbon here. Whereas for, hold on, in acid hydrolysis, you have a weak nucleophile. So first you have to protonate your carbonyl, and then the reaction takes place. But in all of them, it is addition to give you something tetrahedral, and then elimination where the group leaves and you have your structure. All right. Yes, the last two or so things. Acid chlorides are made from acetic acid. Similar reaction, we are going to make this into a good leaving group, and we're going to have our chlorine come in and displace it. So our reagent, thionyl chloride, we would have been introduced to it some time ago when we were looking at how to make alkyl halides from alcohols. And in alcohols, it replaced an OH with a halide. Well, similarly here, it's going to replace an OH with a chloride. Right, so just like what it does for alcohols, it does for carboxylic acids. So our OH is replaced with the chlorine from the thionyl chloride to give us our acid chloride. We form sulfur dioxide gas, and we form HCl gas. So the little arrow is supposed to indicate gas being evolved from our reaction mixture. And so here's the mechanism showing that the OH is being converted to a good leaving group. And then we have our nucleophile coming in. Addition, we form this tetrahedral intermediate, and then we reform our carbonyl, and we have elimination and lose all of this to give our acid chloride. So the same mechanism is repeating itself over and over. Addition, followed by elimination to reform or carbonyl group.
I don't understand this addition. Miss why it look different.
It looks like, all right, remember for other additions, we would have protonated one of our oxygens or done something to make this a good leaving group. Well,
Yeah.
to make the OH a good leaving group, there's no protons around. So what happens is that the oxygen reacts with the sulfur, right? So that's what this arrow is showing. The oxygen reacts with the sulfur. Instead of the oxygen reacting with a proton, it's reacting with the sulfur here. And we're forming an oxygen-sulfur bond, and we are displacing a chlorine, right? The chlorine leaves. And now this, let me get a pencil. All of this is a good leaving group, right? So this first part is to make the OH a good leaving group. And then the chloride can come in, and we're forming a carbon-chlorine bond. We're breaking this pi bond. We have this tetrahedral intermediate, and then we reform the pi bond. And as we're forming this bond, the most polar bond is going to break, which is this carbon-oxygen bond. And so it leaves to reform sulfur dioxide. Sulfur dioxide looks like carbon dioxide, where you have the SO2, the S double bond O, S double bond O, and you form that, and you've also formed some chloride that goes off. So we have our acid and we have our acid chloride. Yes, Casella? Casella? Oh, you had a question? No?
Yes, miss. Yes, miss. Sorry. Is on the carboxylic acid, do we lose the hydrogen here when it's been attached?
Oh, this hydrogen, where did it go? It should still be here.
Yes.
Let me
Oh, okay. That's fine.
draw it out. It should still be here,
Okay.
right? And then it's going to, when this leaves, the chlorine is going to take it to form the HCl, right?
Oh, okay. Great.
Yes.
Thanks.
Yep. So quick question, out of these two, out of your carboxylic acid and your acid chloride, because time is upon us, which one do you think is going to be more reactive?
The chloride, miss.
Okay, why?
It's because you have a something that is a chlorine anyway. But kind of you have a strong in negative inductive effect, miss. So you really pull up, miss. You can form an acid.
So it can
Yes,
form
something
whatever
along the
product.
line.
Okay. All right. So let's neaten that up a bit. Chlorine is more electron withdrawing, as you're pointing out. So it is pulling. This bond is going to be, the carbon-chlorine bond is going to be more polarized and weaker than the carbon-oxygen bond. And yes, Nadisha, it is also a better leaving group. And so usually that's what we do in organic chemistry. We convert our acids into acid chlorides when we want very quick reactions. And there's also something we convert our acids into that we'll see in a bit. If we want to make amides, this is not the best way. We just spoke about this not being the best leaving group. But what else? If you have a carboxylic acid and an amine and you mix the two of them together, what's the thing that you're going to generate instead of your amide? Anybody? If you react an acid and an amine, what is the first thing that we're going to form? We're going to form a salt. We know that this is our acid. We know our amines are organic bases, right? So we're going to form an ammonium salt. So this is not the optimal way to form an amide. The best way would be to convert this OH into a better leaving group so that our amine can react. So we could have converted it to an acid chloride, or we could also convert it to an anhydride. So an anhydride, we see that we have a good leaving group in all of this right here. And so if we convert our acid to an anhydride, it is going to be more reactive than our acid and give us the product that we want. So we form an anhydride from two molecules of acid. They don't have to be the same. Usually they are, but they don't have to be the same. So an acid reacts with another acid. We lose water and we form our anhydride right here. Notice that we've lost water. But once again, this is not the most optimal way to make an anhydride, right? Because to form this carbon-oxygen bond here, it means that one of these oxygens has to act, let me get my, one of these oxygens has to act as a nucleophile, right? And we need to lose all of this, which we know already is not a good leaving group. So what way could you suggest to make an anhydride starting from an acid and something else? What could we react our acid with that has a good leaving group that would allow us to make an anhydride? Anybody? We could react, yes, we could use thionyl chloride, but we would use thionyl chloride to form something first, which is what we would react with our acid. What's a good leaving group we could have here? Instead of OH, what's a good leaving group we could have here? We just talked about it. We could have water, yes, but even better.
A chlorine is wrong.
We could have a chlorine, right? So the easiest way to make an anhydride is to react an acid and an acid chloride, because chlorine is a better leaving group, and we get our product here. All right, folks, it is 6:05. I think we have, wait, sorry. Yes, so this is just showing you our acid reacting with our acid chloride. Once again, addition, we form our intermediate, elimination, and we have our final product. So we will talk about amines next week. Feel free to go through the recordings, go through the lecture notes, practice your mechanisms, and we will talk again. If you have not submitted your labs, please do not wait until 11:45 to try and submit, and then you want to email me and say that you're having problems. At 11:45 p.m., I will be awake. All right, folks, enjoy your weekend, and I will see you next week. All right, so let's stop recording.